Hey y'all, so in this next video I'm going to go through an example of how we can use a system to help us solve a problem. Now for this specific video, I'm going to show you how we would do it without a system first, and then I'll show you how to do it with a system. Now I'm choosing this specific problem because this specific problem is fairly straightforward without a system. You can do it without a system, but it's a little bit easier. I want to present that to you in an easy situation because that way you know that you should not really do it in a more difficult situation. All right, so here we go. We have two blocks of mass 4 kilograms and 6 kilograms that are joined together by a string. They're at rest on a frictionless surface. So you can see that in the diagram here. If a force of 100 newtons is applied horizontally to one of the blocks, then we want to find the acceleration of each block. All right. Now, if I was not using a system here, then what I would need to do, I notice that I'm thinking about forces, I'm thinking about masses, I'm looking at acceleration. So because of that, I would go ahead and I would draw a free body diagram for each block. Okay, so I have the 6 kilogram block, and I would have the force of gravity down, and I would have the normal force of the table up. Now I'm going to label this as Fg on the 6 kilogram block and the force normal of the table on the 6 kilogram block, right? Because I'm also going to have those same two forces over here, and I want to make sure I identify that those are different. Obviously, I also have the tension, okay? For the 4 kilogram block, we would have this. So we would again have the force of gravity on the 4 kilogram block. That should be a little shorter than this one, right? Because it's only 4 kilograms instead of 6. And then I do have the normal force on that 4 kilogram block, which again should be a little bit shorter than that one. Maybe I'll make this a little bit shorter just so it's clear. These two are equal. These two are equal, but they're not equal to each other. We have the tension of the string, which would be pulling to the left. Now that should be the same as this tension right here, right? So those two are the same. That's why I'm using the same exact letter for both of those. And then I have some force, which is that 100 Newton force pulling to the right, okay? Now the question is, can we find the acceleration of each block? Now acceleration, of course, is all happening in the horizontal direction. And so I'm going to go ahead and write out the horizontal forces here. Okay, so for block 6, okay, I'm going to go sum of the forces on block 6 equal the mass times the acceleration of block 6. So I'm putting that subscript on there, the little 6, to remind me that I'm working with just this one right now. Okay, so the sum of the forces just horizontally is just going to be tension. So I guess I could label this as 6 horizontally, okay, if I want to be extra clear. I've got the tension, which is pulling to the right, so I'll make that a positive. So I'll go tension. And then these two are equal. They cancel out, and they're not horizontal anyway, so we're not going to worry about those. Equals the mass, which is 6 kilograms, times the acceleration of the 6. All right? So that would be the first one. Now you'll notice we do have two unknowns, which means that we are going to need a second equation. So if I go to do a second equation now, then I would look at this one. Okay, so for the 4 kilogram block, so I'm going to do the same thing, but now I'm going to do it for the 4 kilogram block. I have tension, but this time tension is going to the left, so I'm going to go negative T. I've got this force to the right, that 100 newtons, so I'm going to go plus 100, that force right there. Those are the only horizontal forces. And so then that will be equal to the mass, which is 4, times the acceleration. Now, if you recognize that those two accelerations will be the same because they're connected by the string, so they're both going to accelerate in the same direction, right? I will notice that this one is to the right, so that's positive. And then this one is also accelerating to the right, so that will also be positive. So I'm actually going to remove my subscript here, the 6x, because that's actually the acceleration of both blocks. And so I want to recognize that those two are the same, right? Now, at this point, we see that we have two equations with two unknowns. the tensions are the same, the accelerations are the same, and so you should be able to go through and solve this using a system of equations, right? Now, to do that, I'm going to just say, well, I see that tension is equal to 6A, so I'm going to put 6A in for the t there. So I'm going to have negative 6A plus 100 equals 4A. I'll add the 6A to the other side, so I'll have 100 equals 10A. I'll divide by 10, and that will give me 10 meters per second squared equals A. All right, so I can do it. I can do it by separating them out and doing one and the other. Now, this was a little bit easier than some other ones that you will see because they were both completely horizontal. As soon as you start to get things that are on a ramp, that have a pulley, that have, maybe you have a mass on the table and masses hanging off the sides, or maybe there's 3 masses, like the one we did in class, remember? It does get a lot more complicated to do this piece of it, all right? And so that's why I'm now going to show you a second method, which is the method that I would probably use if I were trying to approach this question on an assessment, all right? So give me just a second. Let's erase most of what we have here. All right, so now let's look at it as a system, right? In a system, we group objects together. Now, if they're connected by a string, that's a pretty good reason to group them together, right? We also sometimes, if we have a single object that's somewhere in the middle, splits into 2 or 3 or 100 pieces, we might treat those pieces as a system to recognize what is happening to the group instead of what's happening to each individual piece. We can obviously do like what we just did before. We can break it into individual pieces, but sometimes the more important thing is what is happening to the center of the group, what's happening to the group itself. So if I were going to do that, then I would group these two together, okay, as a system, all right? Now, in order to do sum of the forces equals MA, and I am still looking in the horizontal direction, then we're just going to look at the horizontal forces, and we're going to look at the forces that are on the outside of our object, right? So looking at the 6 kilogram object, we have the force of gravity down, we have the normal force up. Now we could draw those in, but we recognize that those two are going to cancel out, right? So I'm going to go ahead and draw them in. So FG on the 6th block and Fn on the 6th block. Those two are equal. They're actually going to cancel out, okay? We do have the tension, but the tension is what we call an internal force. It's inside of my system. So it can cause these objects to change their motion, but as far as the system as a whole, forces on the inside cannot affect the overall system. Now, in some ways, this kind of makes sense because if tension is pulling with a specific force here, tension is going to pull with the same exact force in the opposite direction. So therefore, some pieces of the system will feel a force this way, other parts of the system will feel a force in the other direction. Those two will cancel out, and it will end up meaning that it really doesn't matter. All right, so I'm not even going to look at the tension because it is what we call internal. Okay, again, we have the force of gravity on the 4 and the normal force on the 4, which again, those two are equal because there's no other vertical forces. It's not accelerating vertically, right? And so we know that those have to be equal. So what we come down to is that the only external force we have is this 100 newtons. If there was friction, maybe I would have another force kind of opposing that motion going in the opposite direction. But from the way it is right now, we recognize that the only external force on our frictionless surface is that 100 newtons. And so therefore we're going to go the sum of the forces, which is 100, equals the mass. Now remember, this is the mass of my system, so it'll be 6 plus 4, okay? And then times the acceleration of the system. And what you're going to notice is that we simply just go, well, that's 100 equals 10a. I divide by 10, and I get 10 meters per second squared equals a. Right? Now, even though it was fairly straightforward to do the objects individually and it wasn't all that difficult, I think you'll recognize that this is easier than that was, right? The only hard part is being able to think about it as a group, as a system. And so we're going to have some other videos that'll go through that, and we'll talk about treating things as a system to help us get comfortable with that idea. But in the big picture, you want to be able to do that because, yes, it will simplify things, right? And very often, once we have this, then maybe they'll ask us to do tension. And so for tension, we would have to do a free body diagram for one of our blocks individually, which would then allow us to solve for tension, right? And so a lot of AP questions, especially, IB does this as well, but a lot of them will say, well, find this first, find the acceleration, and so you use the system to get that, and then they will ask you to find one of the individual forces that will require you to deal with one single object, because they want to see, can you go back and forth between this big idea, thinking about it as a system, versus a single object and thinking about it in that way as well. Okay? So I hope that was helpful. We'll see you next time.